volumes are useful for students when they become homeowners, and I have to maybe pour a concrete patio, and I know the area that I want my concrete patio, but I don't know how I change that to a volume to be able to order the concrete, because I don't want to have to order 2 batches of concrete, because then I have to pay 2 delivery fees and stuff like that. Does that make sense? And getting to there, though, I think because of where we're at right now, just getting our feet wet with probability in the last couple of days, I want to go back to area and attach it to probability. And we refer to this as geometric probability, which I view it as, and all these questions can be viewed this way, so you're going to hear me say this a lot. If I were to, let's say, take my white or my smart board up there and ask you, what is the probability, let's say that's a circle, and I say, what's the probability that I close my eyes and I take a dart and I throw it at the dartboard, okay, and I know I'm going to hit the dartboard, so I have the condition that I'm not going to hit anything outside the dartboard, because that could or that will change how our probabilities are calculated. But I know that I've hit the dartboard. So I close my eyes, I throw it, I hear it hit the dartboard. Now you ask me the question, what's the probability that it landed in the circle? Okay? That's what today is all about. And every question we do is very similar to that. But the probability that it lands in that circle would be the area of that circle, because that's the favorable outcome. Does that make sense? Compared to the possible outcomes, which is the sample space, which is the area of the dartboard. Okay, so we'll try to investigate that as we go through today. We've already talked about definition of probability. It's the likelihood or the chance of an event occurring. We talk about the event as probability of that event with that notation there with capital P. So if we're talking about putting all names in a hat, pulling out a name, probability, I pull my name out would be capital P of Mr. Fay. That's something we've talked about recently in the last couple of days. This is classical probability. Okay, classical probability refers to taking favorable outcomes and divide it by possible outcomes. Okay, favorable outcomes is the number of items in your sample space that are aligned with the desired event. Number of possible outcomes is the number of total items regardless of their alignment with the event. Okay, this is the number of possible outcomes is often referred to as the sample space. So if I'm talking about that scenario that I started the class off with, landing in the circle is the number of favorable outcomes. That area would be the numerator here. Okay, the sample space is the entire whiteboard. That area would be the denominator. And if I evaluate that out to a decimal or a fraction, or whatever, that would be my probability. Probability is 0 to 1, inclusive, meaning I can't have 0 and I can't have 100%. But that gets us, so that's just a refresher of what we've been talking about in the last couple of days. Geometric probability. Geometric probability, same idea, but now we're using geometric concepts and geometric models to solve certain probability questions. So the geometric probability points on a segment or in a region, okay, of a plane represent outcomes. All right. So the geometric probability of an event is a ratio that involves geometric measures such as length or area. So those are the two things that we're going to talk about: length and area. Okay, and convert those geometric concepts over to a probability. So we'll see some examples here. I think the best way of doing this and understanding this is to go through examples. Okay. All right. So when they talk about a length, so it says point S on segment AD is chosen at random. Okay. So I'm going to, let's say, so here's the idea that I close my eyes and I'm going to throw my dart at the line segment up there, and you tell me, Mr. Fay, you just landed on the line segment. What's the probability that you landed on B to C, or on that interval from B to C? Does that make sense? Okay. So the point S on AD, so S is my dart, okay? And then I want to know what is the probability that S landed on this red segment BC? Well, that probability is the comparison of the length of BC to the entire length of the segment. Does that make sense? Okay, my sample space, I can only land on the segment, so I can land from A all the way up to D. But the probability that I landed on BC is how big BC is compared to how big AD was. Okay. Now, that can, and we'll do an example of this, just a very simple, you'll see some of these in your homework. It says point K on ST is chosen at random. What's the probability that K lies on QR? So I want to find what is the likelihood that when I throw a dart at this number line, knowing that I hit the number line, what's the probability that it landed on QR? Well, how big is QR? How big is QR? The length of 1, 2, 3, right? I mean, you counted the tick marks, right? Starting with this one, but the length is 1, 2, 3. You can find that length by subtracting the endpoints, 8 minus 5. But the probability of landing on QR is equal to QR's length divided then by ST's length. So QR, you told me, was 3. How big is ST? Careful. Subtract the endpoints to get the distance. 12. So then reduce that, I get 1 out of 4. Okay, so that 1 out of 4 tells me that if I close my eyes, I got 4 darts. And I throw it, and I know that all 4 darts hit that that line segment S to D. One of them, theoretically, one of them should be in QR. Does that make sense? Now, in actuality, in the experiment, maybe 2 of them landed in QR. Maybe all 4 of them landed in QR. Okay? But if I were to do this thing 1,000 times, or 100,000 times, or 1,000,000 times, then 1/4 of those times, the dart is going to land in QR, and the 3/4 of the time, it's going to land in the other parts of that segment, S to T. Does that make sense? Okay, now that idea, okay, that's great. Whatever, we compare 2 lengths and get a probability. How's that applicable to us? Okay, you ever been driving down a road and you're coming up to a stoplight and you wonder what's the probability that I'm going to make it through this stoplight without changing? You never done that? Okay. You've never gone through and maybe been in a hurry going somewhere, and it seems like, maybe going down Elida Road or Harding Highway, and you hit every single red light. Well, what's the probability I hit every single red light? Well, those red lights are on timers. Okay. And if we know, and they change per the time of day. So if you're on like Elida Road at like 3 in the morning, you can fly up and down that without hitting a single stoplight. Okay, but when there's more traffic out there, obviously they got to change the sequences so that traffic is safe. Yeah, so there's pressure sensors in the pavement as well too, especially a lot of those places in which there's little traffic, like late at night or early in the morning. There'll be pressure sensors, so if somebody is there, that they're not waiting forever. Does that make sense? But I'll give you a scenario here or an example like this, and how it's not related directly to stoplights, but it's the idea of if I know something runs on a particular schedule, okay, I can figure out what the probability is of having to wait a certain amount of time. Okay, so a commuter train runs every 25 minutes. So if a commuter arrives at the station at a random time, what is the probability that the commuter will have to wait at least 10 minutes for the train? Okay. So what this means here is at 0, there is no train. Okay. The train has just left, and we start the timer until when the next train shows up. Does that make sense to everybody? Okay. So we want to know, what is the probability they have to wait at least 10 minutes? So if I have to wait at least 10 minutes, think about this. If the train shows up on the 25th minute and I show up on the 24th minute, did I have to wait at least 10 minutes? No. If I show up on the 20th minute and the train shows up on the 25th minute, did I have to wait at least 10 minutes? No. Okay. What about now? What if I highlight that? Did I wait at least 10 minutes? Yes. Okay. So just think about this. So a lot of people, this is where people get mixed up. That yellow or red, yellow, green, that green segment is showing the region of this time interval that I would actually have to wait less than 10 minutes. Does that make sense? If I show up in the green, then I will wait less than 10 minutes to get on that train. So then, does it make sense that if I show up right here, and let's say 3 minutes, would I wait at least 10 minutes to get on this train? Yeah, I'd actually wait, 22? And what if I show up at 10 minutes? Do I wait at least 10 minutes to get on the train? So does it make sense that this purple region here is the times in which I have to arrive and wait at least 10 minutes? So those are the numbers, those 15, that segment length is the favorable outcomes. That is waiting at least 10 minutes to get on this train. So that's my numerator, and I have the opportunity to wait 0 to 25 minutes, right? So it's 25 minutes for the entire train schedule. So that's a start and end point for the two. So right at 15, so when it says at least 10 minutes, that means equal to or greater than, right? Okay. So because of the equality aspect, then 15 would be included, and then the 15 minutes and 1 second would be in the green. Does that kind of make sense? And with probability, the idea is that even that equality doesn't really, I'm not going to get into it, but doesn't play a huge role in probabilities. So 15 out of 25, or 3/5, or 60%. Okay, so let's say that I've got to be somewhere in a certain amount of time, and I don't want to wait on this train, but I don't schedule things. I'm going to the train station, and I got a 60% chance that I'm going to consume 10 minutes just waiting. Does that make sense? Okay. Probability allows you to maybe plan a little bit, maybe make decisions with a little bit more data or information than you would without it. Okay. So that's the same idea. Like I said, lights. Stoplights are programmed. And now I don't think anybody's driving down and saying, okay, now what is the probability that I'm going to make this next light? But that's all part of that situation. So we'll see some of those questions in your homework. The way I've got it set up is most of them are like this, where there's really no context, no story to the problem when we're talking about these distances. But the ones that do have context to them are more like this. Okay, we're talking about areas. Okay, and this is the dartboard idea, kind of more functional dartboard that you're more used to. Okay, people aren't really used to a number line dartboard, right? Okay, usually you have a circle or a rectangle or whatever. Okay, this says if I have this region R and this region N inside R, okay, and I want to know what the probability that point S falls in region N. So close my eyes, I throw it, you guys say, Mr. Fay, you landed in R. What's the probability that you landed in N? Okay, would be N's size and area divided by R's size and area. Okay, because N is the favorable outcomes, and R is the total number of places that I could have chosen the point to come from. So what happens with this stuff is they start giving you essentially these dartboards that are made up of different shapes. They might be, the next one we see a square and a circle. Sometimes you might see like a hexagon inside a circle. You might see concentric circles, kind of like a traditional dartboard. And we don't have specific formulas for the entire situation. So we have to piece together a couple concepts. Okay? So here it says a circle is inscribed in a square. Remember what inscribed means? It means we've got that point there, that one, and that one. They are tangent, correct? So circle is inscribed in a square. Point Q in the square is chosen at random. What's the probability that Q lies in the shaded region? So the way I like to interpret that is to close my eyes, throw my dart, and you tell me, hey, you hit the square, and then you ask me, well, what's the probability that it maybe landed in one of these yellow regions? So what's the probability maybe I chose that, I got in that area? Does that make sense? Okay. Or maybe it was that one or that one. Okay. So what we do is we have to find the probability of landing in the shade, which would be the shaded region divided by the area of the square, correct? If I look at these shaded regions, and I don't even know what the names of these shapes would be, but they're kind of triangular, right? But they're not, okay? So we don't have a formula for that area. We don't have a specific formula for that area right there. Say again? Okay, so we can find the area of the circle, right? Okay, so this is saying, when this says 6 here, it's talking about the length of the square, right? Okay, so if I look at the circle, that radius is going to be 3. So the area of the circle, remember the area formula for a circle is pi r squared, right? So my area of my circle, is 9 pi. Is that okay with everybody? Okay. What's the area of my square? 36. Okay. So if I gave you like a 36 square centimeter piece of paper, and I told you to cut the circle out, the inscribed circle out like this, and I asked you to come up with the area of paper that you would be left with, you'd be left with these yellow pieces, right? That area would be 36 minus 9 pi. Remember, minus because you cut out the circle, right? Does that make sense, everybody? So that's the idea, that you have to use multiple formulas with a plan, and the plan here was we have to subtract them to come up with an irregular areas formula. Okay, so now that'd be 36 minus 9 pi. What was the area of the square? 36. Because it's the area of the shaded region divided by the area of everything I could hit. Because I could throw my dart and hit right there, and that'd be part of the square, right? So we're asking what percentage or what proportion of the square is the circle. Does that make sense? Okay. Or what proportion? I guess that would be the idea if we're trying to land in the circle. I'm really asking what proportion is this yellow stuff of the square. Okay, and that's this right here. Now, can I cancel the 36? No, I can't. Okay, so that's the exact area. If we want to, you can simplify. You could take a 9 out of the top and the bottom. So because there's a 9, you can write it as 9 times 4 minus pi. Does that still give me 36 minus 9 pi if I multiply that through? and the bottom is 9 times 4, right? So 9s can cancel. I could write it as 4 minus pi over 4. But they're never going to ask you for probability like that, because we present our probability as percentages or decimals, right? Or a, sometimes like a 2/5 or something like that. But that denominator and numerator are easy to realize in comparison. So something like this, they're going to ask you to type it in. So 36 minus 9 pi. And we'll divide that by 36. Yeah, 21.4, 21.5. Okay. So what we're saying there is that of this square, the yellow is 21% of the area. Does that make sense? Okay. Meaning if I threw 100 darts at this thing, theoretically, 21 of those 100 darts are going to land in the yellow. Okay. Now, will that actually happen? Probably not. Okay. There's also the question, and then this is where probability, guys, gets we can get sidetracked, go off on a tangent. We enter the realm of probability that gets very, very complex, and you can start using calculus and very high levels of calculus to determine probabilities. But the idea is, okay, well, what if I have skill? What if I don't close my eyes? Because when I close my eyes, the idea is that I eliminate skill, right? Does that make sense? But let's say I have skill, and I'm very good at playing darts. Now I skew the probabilities, don't I? Okay. So those types of things are things that always think about, but that is something that you start to talk about in, like I said, like college level, graduate level probability classes. Huh? No. Nope. I probably won't even hit the square. Let's do this one. This one is generally a question that people struggle with. So this is a legit dartboard, right? Okay. It says an archery target has 5 colored scoring zones formed by concentric circles. Concentric circles just means that they share the same center, right? Okay. So the target's diameter is 122 centimeters. The radius of the yellow zone is 12.2 centimeters, and the width of each of the other zones is 12.2 centimeters. If an arrow hits the target at a random point, what's the probability that it hits the red zone? Okay. Yeah, so this is a tiered question. So what I want to talk about real quick on the side here is what this shape is. Okay, when we talk about concentric circles, if I'm looking at okay, you said ring, right? Okay, it looks like a ring, looks like a donut, correct? But the red region that I'd be wanting to hit here okay, so that would be the area that I'm interested in, correct? But does everybody see that if I find the area right now of everything that is red in this picture, so the area of that circle, does that make sense? And then find the area of the white circle, what can I do with the area of the red circle and the area of the white circle to get what is just red right now? I could subtract them. Does that make sense? Okay. Now, there's another way of doing it. Okay. Does anybody know what this? You said ring, which isn't a terrible word for this. Does anybody know the math word for this shape here? It's called an annulus. Okay. Which is essentially like a donut or A donut in actual like geometric terms, because it's 3D, is called a torus. But this is called an annulus. Okay. If I want to find the area of this, just like you told me, okay, so I'm going to say, let's go back to, if I want to find the area of the entire, can everybody visualize the biggest circle here? Okay. Is it going to have a radius out like that? Does that make sense? That would be give me the whole, everything that was, when I shaded it all red, that would give me that area of that circle, right? I'm going to say that the area of that circle, so I'm going to just say the big circle, is pi r squared. Now I'm going to use a capital R because I'm going for it to be the big circle. Does that make sense? So capital big R compared to big circle. Does that make sense? Everybody okay with that? All right. So that would be the area of the big circle. What would be the area? Let's look at this white circle. That R would be, let's call it lowercase r. Okay, so small circle would be pi small case r squared, right? Which one of those is going to have the bigger area? The big circle, right? So if I want to find the area, so you told me, Jagger, earlier that you're going to subtract the two circles, right? Well, let's do it. Let's subtract these two circles this way, without knowing what R, capital R, and lowercase r are, but we know this one's bigger. So let's go pi r squared minus pi lowercase r squared. What do they both have in common? Careful. The pi is not squared here. Only the r is squared. But they both have pi, right? If I take a pi out of these, I'm left with r squared, right? Capital R squared. Take a pi out of this one, you're left with lowercase r squared, right? There's an area formula. And the reason I show you this is because you don't need it. You can do this without this area formula. But finding the area formula for an annulus is going to be something that they repeatedly ask us to do in some of these questions. So that's maybe the shortcut to doing it. So that would give me the area that is just colored in red here. Does that make sense to everybody? Okay. So let's kind of see if we can figure out what these values are that they're giving us here. It says an archery target has 5 colored zones. The radius of the yellow, so the radius of the yellow right now is 12.2 centimeters. So this here is 12.2. Does that make sense to everybody? It's a small radius. Okay. It's saying the width of each of the other zones is also 12.2. Now, when it says width of the other zones, that's talking about the width of the annulus. That's talking about like that distance right there. Does that make sense? Or it's talking maybe about that distance right there in the blue, or that distance there in the black, or that distance there in the white. Is everyone okay with that? So those are when it says the width of the other zones is 12.2. That's not the radius of the other zones. Okay. But if I look at this, how big was that radius in the yellow? 12.2. And if I add another 12.2 to it, is that then the radius for that right there? So 24.4 is going to be big R. Well, careful, because so it's going to be, so it's because order of operation says 12.4 squared minus 12.2 squared. What does the order of operations tell us we have to do first here? We have to square before we do subtraction. So it's not, so this quantity here is not the same thing as 12.2 squared. Okay. So that would be the area that is all red here. Okay. Now what we want to do is we want to find the area, and we'll take our calculator and change that to a decimal here in a little bit. Now we want to find the area of the entire target. Well, okay, so this was 12.2, right? There's another 12.2. There's another 12.2, another one, and another one, right? Is everybody okay with that? They're talking about colored rings, though. So the way that I'm interpreting this is the way that you see this white line there, and you're seeing this black one there, right? This whole blue thing they're saying is 12.2, not each individual part of the blue one. Does that make sense? So yellow is 12.2, red, everything that's red is a total of 12.2, everything that's blue is a total of 12.2. So there's only 5 rings. Does that make sense? What do you mean add up to 122? Well, because this is only 5 of them, so the diameter is that times 2, right? So I didn't pay attention to that. You can use that if you want to find the area of the entire circle. Sometimes this won't be given. I don't think every time in your homework that number is given as the diameter. So you can say 12.2 plus 12.2 plus 12.2 plus 12.2 plus 12.2, right? Or you could take that number and divide it by 2, and that gives you the radius. So that is 61, right? Okay. So the area of the target is equal to pi times 61 squared. Okay, and that's all the possible places that I could hit the target, right? That's the sample space. That's the denominator. Okay, 61 squared pi is the denominator. Pi over or times 24.4 squared minus 12.2 squared is my numerator. Do these pi's cancel each other out in this situation? They do, because it's all multiplication here, right? Which doesn't matter. If you want to do that cancellation, you can. I'll show you that it doesn't matter. But we've got pi 24.4 squared minus 12.2 squared all over pi times 61 squared, and I get 0.12. Okay. Now, like I said, if I cancel these pi's out, do I still get 0.12? So they can cancel. Okay. So 12% chance of landing in the red. Okay. Now let's just think about this. And I'm just going to do it on Desmos. Because pi times 61 squared was hitting that's the entire target's area. Okay? Let's look at the yellow's area. Wasn't that 12.2 as the radius? Okay, so now if I want to hit the yellow, it's a 1% chance versus, oh, yeah, I'm sorry. Thank you. Okay, so there's a 4% chance of hitting the yellow in comparison to 12% chance of hitting the red. Does that make sense? So I've got 3 times more likely to land in the red than I am in the yellow. And that makes sense for how we understand, and we've all thrown a dart or tried to hit a bullseye, right, and something. That's the hardest thing to do, correct? Because it's the smallest area for you to address in comparison to the other areas in the target. Okay? So as we move out, so we did the yellow, we did the red. If we did the blue, that area is going to be bigger than the red, so the probability will be greater. If I add it all, if I did the probability of the yellow plus the probability of the red plus the probability of the blue plus the probability of the black plus the probability of white, what would that all add up to? It'd all add up to 100%, or 1. Is that okay? So they bring in different shapes, okay, different scenarios. What's the probability of landing in the yellow here? So if I look at the yellow is a what? Okay, the yellow is a circle. So let's find the area of the circle would be pi r squared. What's r going to be in this case? R is going to be 9. Now that's special for a hexagon. That's terrible. That center right there, okay, which is going to be that right there, which is my apothem, if you remember that word, is going to be half of, because of the even number of sides for the hexagon, that apothem, which is my radius of my circle, is always going to be half the total height, I guess, here of our hexagon. So R is 9. So we've got, 81 pi as the area of the circle, correct? Now I need to find the area of the hexagon. Does anybody remember the area formula for a hexagon? Okay, so you're going to try to find the area of the circle or the triangle in here and multiply it by 6. That's fine. I'm going to go 1/2 apothem times perimeter. You guys remember that? The apothem said was 9 here. Okay. The perimeter is 10.4 times 6, right? So what's 10 times 6? 60. What's 0.4 times 6? If I go 0.4, so this is the way that I do this in my head. Because multiplying decimals is hard in your head, right? Move this to a whole number. So you moved it to the right 1 decimal, right? So you get 24. So your decimal will be there, right? Now move it back how many moves you made. So you move it back. So it's 2.4, right? So if I had like 0.6 times 0.2, I would move that there and I would move that there. So I get 6 times 2, which would be 12, right? But collectively, how many decimal places did I move? 2, so I move it back to 0.12. Is that okay with everybody? So 2.4 plus 60, 62.4, right? So if I multiply those things together, okay, so that's the probability, or so that's the area of the hexagon, right? The area of the circle, which was our favorable outcomes, was, what we say, 81 pi? So a 91% chance almost of landing in the circle. And now think about this. Does that, per how big that circle's area is compared to the whole thing, does that make sense? It's a reasonable answer, right? Yes. What would be the probability that I land in the white region without doing any more further calculations? Okay, so it would be 1 minus that, right? What would be the probability that I land just in that one right there? I would divide it by 6. So you see how you take this number here and divide by 6. You see how you can kind of parlay one calculation or one answer to a question into a maybe more complex or more stratified question. And just hopefully through logic of, using complements or division, you can do that. So something we can feel comfortable with. All right. So geometric probability takes our knowledge about geometry and our area formulas generally, and our knowledge about probability, and merges them together. Okay, so there should be, it's 10.8. 10.8 is this section that you're going to see in Math Excel. It is due Friday. Okay. How many of you are taking a test tomorrow? All of you? Okay.